Okay then. Let's make sure this works. Yep, it works. Okay. So let's turn that down a little bit. Just got some Frank Sinatra going on in the background. Okay, so it sounds like people had some problems with this, but overall we did pretty well. It was a little bit of a head scratcher. Hope you can hear me well. So I'm going to go over this, but I'm going to do like I did with the last one where I go over some important concepts first. So you can go ahead and grab ourselves Excel. So it feels like a lot of people were not checking their... So when you do this, it's a good idea to have your notes with you because you're probably not going to have everything memorized yet. Hopefully by tomorrow you have at least most of it memorized. But I think the first thing we want to go over is first that how molarity works, right? So molarity equals moles over liter. So if I have any two of these numbers, then I can find the third, right? If I have molarity and mole, I divide by molarity. This is also divided by molarity. I multiply by liters on this side. I have liters equals mole over molarity. So I'll change it to be this. Oh no, sorry. Liter equals mole. So if I have mole molarity, I can find the number of liters of the substance. And you can do this with any of these. And this is pretty much the first like 5 or 6, maybe 7 problems. So just knowing this is already most of this homework. Yeah, see, these are almost entirely just molarity problems. Just making sure you do the math properly. It's not too much problem. Then the rest of this is just it's just theory. So isolated system, nothing it doesn't, no energy moves. Knowing the first law of thermodynamics, what it means. Then we do have change in E. So this one has, I need to get my delta sign. Delta sign. Here it is. No, it won't let me grab it. No. There we go. There it is. Grab delta. So we have, oh, it's a little bit big. Let's make it smaller. How big is this? 11? Okay. Yeah, I'll put to 11. And probably, ooh, that's weird. Where's Calibri? Wherever it is. Here it is. Okay. Now let's write in the font. We can copy it again so we don't lose it. And then we have change in E equals Q plus W. So Q is heat, right? So heat in, so something that's endothermic, Q is positive. It's the heat is going in to the system, whatever our system is. W is work. So if our system expands, it did work to expand against whatever's outside of it. So if it's a gas and it gets bigger against a constant outside pressure, then work is negative because it's putting out energy. Energy is going out. It's doing work. If it gets pushed in, it gets smaller, our system gets smaller, or work is done on in some way, energy is going in. So W would be positive in that case. If we put energy in and the system does work, then Q is positive, W is negative. If we take heat out of the system, just presumably by doing work on it, then Q is negative and W is positive. I think most of the time we're usually going to have W being negative. Usually our system is going to do work on all these problems, I think. So like in 10, we put heat in and work comes out. So, see if there's anything else we need to go over. I think we need to go over this equation. Yeah. Probably also do P change in V. Yeah. If the system absorbs heat and does work on its surroundings, its energy. Yeah. So just more theory, more theory. 14 was very odd. Not gonna lie, it was very strange. But anyway, oh right, also yeah. So we want to go over change in E or W. Sorry, yeah, W. So W, this is work done, equals negative P delta V. So what this is pressure and the change in volume, and it does work. And when your system does work, it's losing energy. This is why it's usually going to be negative, because this is what the equation we got. It doesn't have to be, but it usually is. And then it can also be, the equation is also negative delta nRT. So we're going to use both of these, I think. I think that's most of it. If we need another equation, I can put it in here. But I think that's most of it for now. Just knowing how to use these is really important. Oh, I almost forgot. So someone was really confused on, yeah, it was number 10, I think. Here it is. Yeah, number 10. So this equation, when you get your, when you put your three numbers in, this will be in joules. This will not be in joules. This is in liter atmospheres. So when you multiply P change in V together, you get liter atmospheres. Yeah. This is not a joule. However, 1 liter atmosphere, 1 liter atmosphere is equal to 101 point, what's our number? 3 joules. So whenever you have liter atmospheres, you need to convert it by multiplying your liter atmospheres by 101.3 to get joules. So that is important to know. Well, let's go ahead and just do all of them. Yeah, this is very much a knowing how to do it, and then it's easy. And until you know how to do it, it's not easy. So some people had some issues with number 1 just because they were wondering, they just didn't quite understand that this is asking for chloride ions. We don't get chloride ions, we get iron chloride. And when iron chloride, this is what iron chloride looks like, is put into solution, is when it's dissolved, it ionizes, right? So we have Fe3 plus, and we have 3 chloride ions. Oh, that's not the right one. Yep. We have 3 chloride ions. It's asking about this. It's not asking about iron 3 chloride. It's asking about the molar concentration of chloride. Excuse me. So we got iron 3 chloride. We got 0.075 mole. This is only 1 goes in, but we get 3 chloride ions out. So we want to multiply this by 3. So this is the number of moles of the ion that we want. This is not the correct number. We use this number. So we have liters and we have our moles. So as we can see, we just do mole over liters. So we do this divided by 0.225 divided by, and then this is milliliters, you just divide it by 1,000, it's 540, so it makes 0.54 liters. And we get our molar concentration of chloride ions to be 0.417 moles per liters, or molarity. Excuse me. This is a slightly different. So instead of getting moles, we get molarity in this one. So we did these two, and then there's just one more that exists. So we have molarity times liter equals mole. So this is probably the easiest one to do. If you have molarity and you have liter, all you have to do is multiply them together. So we want to know what the number. We want to know how many moles of HCl we have first. That's the first thing we want to know. We want to know how much HCl do we have in these two solutions with these differing molarities. So we're just going to find. Oh, yes, I know. Let's split it up. So let's not do it all at once. So it's not 0.783 times 0.25. Oh, whoops. I typed in that. There we go. That works. Okay. So that gives us 0.19575 moles of HCl. Oh, wait, let's get rid of this. It's kind of in the way. And then we're going to find out how many moles we have in the second solution. So that's 0.203 times 0.6 HCl. So these are our two, the moles in this and the moles in that. So we just need to add them together. Plus this equals. So this is our total number of moles. Now we want to know the molarity of the solution that combining these makes. So we're just gonna add these two volume numbers together. So we just add 783, so 0.783 liters plus 0.203 liters. So the reason we're doing this is that we're mixing these two solutions, and we want to know what their molarity is. The final number of liters is just going to be these two added together. But the number of moles is not just these two molarities added together. We have to find out how many moles is in each of these first. So we did that. So now all we have to do is divide this by this, and we get our new molarity. So now we're doing this equation. Divided by this. And we get our final molarity of 0.322. Remember, your numbers might be different, but if you do the same equations, you'll get the right answer. Ah, yes, this one. So, yeah, let's write our balanced chemical equation first. Let me just copy this. It won't copy perfectly, but that's all right. Let's go ahead and get rid of this. Okay, so we balanced our equation. So we have SrO2 plus 2 HNO3 is converted into 2 waters, and SrNO32. So we start with 0.75 liters of 0.85 molarity SrNO3, strontium nitrate, is formed upon reacting nitric acid and excess strontium hydroxide. So we have the number of moles here. That's what this is giving us in liters and molarity. So we have to calculate it of this what it produces, and it's asking us for how the molarity of what we put in here. So here we only have our liters, which is 0.515 liters of this. But here we can just go ahead and calculate. So we just so this is volume, molarity. So as you can see here, we multiply them together and find the number of moles. So we can't convert molarity. We can't, that's not how that works. So we have to first find the number of moles here, convert the moles, and then convert that back into molarity using the volume. So we can go ahead and put in 0.75 times 0.85. And we get our number of moles. But as you can see, for every 1 mole produced, 2 moles HNO3 went in. So we can multiply this by 2 first. So times 2. So we had 1.275 moles of this that went in. And all we have to do is divide it by liters to find the molarity. So this one equals this over 5.5. So we get a molarity of 2.48 molar HNO3, which is correct. For number 4, so this is another similar problem, but instead of going converting across the equation, we're actually neutralizing. So we have sodium hydroxide, NaOH, plus sulfuric acid. Okay, so that's H2SO4. I'd have to look this up, so do look these up if you don't know off the top of your head. You can in the test, but hopefully they don't give you a bunch of weird ones. So, oh right. So in this equation, we can see that we have 2 hydrogens and we have 1 OH. We need 2 OHs to match each. We need an OH for each hydrogen to make an H2O, and 2 NAs for every SO4s, for every SO4 to neutralize it properly. So we can add the other side of the equation, but in this one we actually don't need to, because we're going from sulfuric acid to sodium hydroxide. So there's just no reason we can, but it's not necessary. So it gives us the molarity of sodium hydroxide. It wants to know how much, what volume of this concentration we need. So it tells us how much sulfuric acid we put in. We can go ahead and calculate that. So this is liters and molarity. We multiply them together. So molarity is 0.3, and our liters is 0.038. Together. So this is the number of moles. We're going to double that because for every 1 of these that goes in, we have 2 of these that goes in. So multiply that real quick. This is the number of moles of an AOH. And we have the molarity of 0.4, and we have the moles of 0.0228. Mole molarity, mole divided by molarity. So we'll just plug that in. Mole over molarity, 0.4. And we get 57, that's 57 milliliters. Divide by 1,000 and you get milliliters. So that's 57 milliliters. And as we can see, that's the right answer. That's number 4. Let's go to number 5. Write a balanced chemical equation. What is the molarity of CaNO3 to mixing 150 milliliters? Okay, so yeah, we do want to write a balanced chemical equation for this one. Because it's the same metal, they're both going to be have a 1 in front of them, because they'll just swap. Or no, they won't. What do they do? Oh, they're on different sides. Well, they're both still going to have a 1 in front of them, but they're going to be on different sides. Ah, okay. I was confused by it. Okay, so we have HNO3 on the side of the equation. Okay, yeah, that makes more sense. Oh, now it works. SH. So we have H2O plus, oh, that's not O, that's 0. Plus, what else would it make? It would make, oh, right, CaNO3. CaNO3. 2. Then it's pretty easy to tell that this is going to have a 2 in front of it because we need 2 H's for each OH, just like the last one. We can put a 2 there. Okay, so we mixed 0.2 molar HNO3 with the same amount of 0.01 molar. So let's just compare these two numbers. So this is the same. This is the exact same number of liters. 0.2 molar. 0.01 molar. This is 20 times less. This is going to limit the reaction. So we don't even have to look at nitric acid. All we need to look at is our calcium hydroxide. So we have 0.01 M, and so it's 1:1, but we're not able to calculate. We're not able to just say that it has 0.01 because we added liquid, right? So what we need to do is we need to find. So we could find the moles, but we don't actually need to because we're diluting this 0.01. We're decreasing its concentration by a half, right? Because we're adding exactly 150 milliliters to 150 milliliters. Gosh, we know that this is concentration. It's going to be halved, so we can just divide. We can just divide by 2. So our new molarity would just be 0.005 because it's 1:1. So we could do more math, but it's not necessary. But if you were to do the math, all you do is use the 0.15 times 0.01. That would give you your number of moles of CaOH, and then you divide that by 300 milliliters, or 0.1 liter, and you get your new molarity. You don't need to, though, because we can see that the concentration is just halved. Wow, that's a really long explanation. That's not necessary. Wow, yeah, that's unnecessary complicated. The products are sodium nitrate, so that's NaNO3, carbon dioxide, and water. Okay. That's the products, so they're on this side of the equation. Sodium carbonate, so that's Na2CO3, yeah, plus, oh, what happened? There it is. Plus nitric acid, that's HNO3, yeah? Yeah. So, okay, so this is just another neutralization reaction. So it gives us the number of, the amount of nitric acid. So we can go ahead and calculate this just by multiplying the volume by the molarity. That goes 0.02218 times 0.1682. Oh wait, 68262. Yeah. Ooh. Oh, and I didn't. Oh my gosh. Hope I'm not doing this on the test tomorrow. Ooh. Okay, so we get the number of moles of HNO3. Oh, we haven't even balanced the equation. What are we doing? We are not awake. So CO2, so it drops an oxygen, 2 hydrogens, 2 NO3 for the 2 Na. We have 2 of these. We only have 1 CO 1 CO2, 1 CO2, 2. Okay, that works. There we go. Okay. So because we have HNO3 and we have this many moles of it, yeah, we're going to divide this by 2 because we need half of these moles to neutralize this much. Or we need half of this to neutralize this, yes, whatever. You get what I'm saying. Divide by 2. And then this is our molarity, this is our moles, mole molarity. So we divide mole Na2CO3 by its concentration that gives us, which is 0.107. Okay, so that gives us 16.8 milliliters, which is correct. Okay. Yeah. That wasn't too confusing, but I certainly had some issues with it, apparently. Oh my. My allergies are killing me. God. We'll dry it out from all the allergy medicines I'm on. Whew. Number 7. What is a molar mass of compound of 25 grams? So this is just saying, so all you have to do in this is calculate the number of moles. So we just multiply. So this is just find the moles. So molarity times liters. So 0.75 times 0.29. This is probably the easiest one on the homework. And then that's our molar. That's our moles. And then molar mass is grams divided by mole equals molar mass. Yeah, whatever. Anyway, so we have moles, so we're just going to divide our grams by it. Our grams is 25 over that. That one's pretty easy. It's 1.115. It's 115 grams per mole, yeah. Number 8 is our first theory questions. So an isolated system means that it can't transmit or receive energy, matter, anything from surrounding X to the system X. Basically, what that means is that it's not touching it. It's not moving heat away or in. It's not doing work. So if it's not touching it, it can't transmit kinetic energy. Heat isn't moving because there's no energy movement. Matter isn't moving it. It just can't because the system won't for whatever reason. It's isolated. And sound waves can't because it has to be touching it. It's just like kinetic energy. The same thing. So none of these are transmitted in an isolated system. None of them flow out. Number 9, I believe it was not the lecture that we had today, but the lecture we had on last Thursday. We got the first law of thermodynamics, which says, law of conservation of energy states. Energy can be neither created nor destroyed, only converted from one form to another. So what this means is that the surroundings and the system together, their change in E must be 0. Or, in other words, the internal energy of the universe is conserved. You can't gain energy, you can't lose energy. Additionally, 1 and 2 are the same thing, right? The internal energy of a system plus the surroundings, that's the universe. The universe is the same thing as system plus surroundings. The universe is the surroundings. These mean the same thing. Number 3, however, the change in internal energy of a system and surroundings have the same. So 0 doesn't have it. So it's 0. The change in the change in energy of the universe, delta U, I guess, is 0. 0 doesn't have a sign, right? So, oh wait, no, I'm wrong. I'm incorrect. I'm completely wrong. What this is saying is that the delta E. So, we need to get this back. I think we copied something. So what's saying is that the delta E of the universe, so delta U is more like it, or delta E of system, and delta, that's so annoying, just type delta E surroundings. It's saying, why is this lowercase? There we go. Why are these putting, what? Stop that. What's this doing? Bad. Okay, anyway. So what it's saying is that this can be positive and this can be positive, right? So what it's saying is that, no, I just want the plus sign. Thank you. There we go. So what it's saying is that the change in energy of the system plus its surroundings, they can both be positive or they can both be negative, right? But this is wrong. The change in energy of, so this would, what this is saying is that the change, just let me type, please. Change in energy U can be positive. Or that change in energy U can be negative. Dang it. There we go. So what the first law of thermodynamics says is that this has to be 0. It can't be positive, it can't be negative. 0 doesn't have a sign, by the way. Just assume that 0 is signless, which is, it is. Just, it's signless, right? So neither of these are 0. So this is instantly wrong. Because the change in energy of the universe, so delta U must equal 0. Therefore, either this has to be positive and this has to be negative, or this has to be positive and inshallah, stupid system. Quiet, you machination. Anyway. So it has to be system is negative, surrounding is positive, or system is positive, surrounding is negative. It has to, or delta U will not be 0. Delta U has to be 0. That's this first law of thermodynamics. The energy universe has to be conserved. So 3 is saying that it can, in some circumstance, not be conserved. So 3 is wrong. So it's only 1 and 2. So yeah, that's just what I'm saying. Yep. Okay. Cool. I'm right. Epic. 10 is yeah. It's not too hard, but a lot of people are having some issues with it. So first, we have a 100-watt heater, and a watt is 1 joule per second. So we have 100 joules per second, and it's heating the gas in a cylinder for 15 minutes, right? So that means we have 100, and then we want to multiply this by first 15. That's the number of minutes. So we now have. We need to find seconds. Sorry. So it's also gonna be second. Well, whatever. Basically, what I'm saying is that we need to find the number of seconds, which is 15 times 60, and we're gonna multiply that, and it's gonna be s over 1 times j over s, which is going to result in j because s over s is 1. So we're going to find the number of joules by finding how many seconds we heated it for. And then that gives us the number of joules, which is 90,000 joules. And this is our N. This is positive, and this is our Q. Q is positive, 90,000. That's 90,000. Okay, there we go. This is our Q, and then it says that our system does work. So W is going to be negative. But what negative is it going to be? Specifically, it's going to be P change in V. So P delta V. So all we need to do is plug in our numbers. And remember, liter atmospheres are equal to 1 liter atmosphere is 101.3 joules. So we have our atmospheres. We have 3.876 times the liters. The change in volume, so the change in liters. So 7 minus 2 is 5. Not too hard. And then we multiply that by 101.3. That gives us joules. So we now have our work done, which is 1963 0.2. So in order to find our change in E, our delta E will equal the Q and W added together. So that's 90,000 minus 1960. So we're going to do the work here. So 90000 minus 1963. Excuse me. We do. That gives us 88,036.8 joules. But this asks us to answer in units of kilojoules. So we do 88 kilojoules. There you go. That wasn't too hard. You just have to make sure you do all the work properly and answer in kilojoules, and you'll get the right answer. Yep, nice. Apparently I'm actually slightly off. Let's see, where am I? Oh, they only used 100. Whatever. You know, I don't care. Apparently they're only using 100 and 700.3, but it's close enough that it doesn't really matter, I don't think. Because it's kilojoules, you know, like, so I don't know. I'd assume just use 100. Probably just use 100 joules to equal 1 lunar atmosphere, since that's what they seem to be doing here. Instead of 101.3. Yeah, just use 100. Wait, no, that's just for a second. Wait, what is it? No, they did. I'm stupid. Sorry. 101.3. Oh, it is slightly different. Well, yeah. I'm just going to use 101.3. That seems to be correct. Sorry, a little bit wrong occasionally. Okay, so this is another theory one. Assuming the gases are ideal, consider the work done on the system in each of the following reactions. 1 mole remission. Silence. Okay, so what's happening here is work is being done when when the volume of a space increases or decreases, that is work being done, right? So negative P change in V. So when things go through chemical reactions, they can increase or decrease the number of liters of gas in space, or the volume. So if the volume change is positive, then work done is negative. But if the number of if the change in volume is negative, then we'll actually have positive work being done. So if you look here, the volume is going down. The change in volume is negative. So our W is actually going to be positive. So it's going to be 3 or 4. And then if you look here, this is 2 moles into 2 moles. So there's no work being done. So it's either 3, 4, or 1. So it's either 3 or 4, right? So which of these is it going to be? So how do we calculate this? This is not too hard. I'm pretty sure, yeah. We're going to actually be using the second equation here. I think you could use P change in V, but I think you'd have to actually use the full Puvner to figure out like the temperature and everything. We're not going to do that. So it gives us 1 mole, which will turn into half a mole. So so it's going to be 1 minus a half, or sorry, it's going to be a half minus 1. So our change is going to be negative a half. Right. No, that's... The change is going to be 1 to a half. Yeah, it'd still be negative a half because the change is minus 1/2. Sure, whatever. Anyway, when the volume is decreasing, then the change is negative and the work is positive. So we're just going to say that this is a positive equation. Anyway, so that's half for n. We can just go ahead and do the equation. Sure. Half times 30. So we're doing this. This is all in Kelvin, remember? So that's 303 Kelvin, and then I remember it, but some people are having trouble remembering, so you might want to try memorizing the R value for the new thing, which is 8.34. And then I don't know if we have to memorize both R values, but I do believe they're going to give it to us. I'm not sure. But anyway, and when we're doing these, it's this form. So it gives us this. So this is the work being done on our system. So the system is gaining energy from this work being done. So this is positive. And it wants us to do it in kilojoules. So just divide by 1,000 is 1.26, and then we get 4. This one's a bit weird, but yeah. Wow, that's long. Anyway, moving on. If a system absorbs heat and also does work on surroundings, it's just saying that Q is positive and W is negative. Depending on which is higher, it could either gain or lose energy. Yeah, its energy may increase or decrease. It's like, This is just knowing that the change in E of a system can be positive or negative. That's all this is really knowing. It can be both, right? So not too hard. Just have to. It's trying to get in your head. I feel like. Don't let it. We're almost getting to the weird one, but this one's not too hard, I think. So this is just saying that this ideal gas is expanding against no outside pressure. So in our notes, I remember. So it says, when an ideal gas expands at a constant temperature, isothermal expansion, there is no change in kinetic energy or potential energy due to intermolecular forces. Isothermal expansion for ideal gas, change in E is 0. So change in E has to be 0. If the kinetic energy doesn't change, then no work is being done. Because it's just expanding, right? So 2 liters at 5 atmospheres, 5 liters at 2 atmospheres, that's 10 liters atmospheres of both, right? Nothing has changed. It's just a gas expanding. Gases do that. So no work was done. The heat didn't change. These are presumably still expanding. And change in H, I'm pretty sure it's just Q. So none of these change, so it's 5. Nothing changes. T is constant. There's no change in molecular kinetic energy. Nothing changes. But what's confusing is here it says that a gas is allowed to extend isothermically against a constant. I thought isothermal expansion was like no external pressure, but that's wrong. But what it still means is that the change in E still has to be 0, but that there could still be something happening if it's against an external pressure. It just has to be 0. It just has to be add up to 0. So I did not know how to do this. I knew that it was going to be either 2 or 3 because clearly something is happening, but wasn't sure which. And then someone said that it was this, and it does make sense because this is in joules. But apparently the way you do it, this is a gas law equation, which is very odd in my opinion. But seeing what they did, that does make sense and is not too hard. So I'll do the work that no one did because no one knew how to do this stupid question that I know of. So we have PV equals PV, so no nRT, just PV. Just Monica. So we have pressure of 5 atmospheres. So we can go ahead and do the work for this. So 5 atmospheres, 2 liters, and then we have against 3 atmospheres. So How does it do this? Right. Okay. So against 3 atmospheres. So we're looking for the new volume. So we divide by this pressure 2. I didn't put down the numbers, but yeah. So this is our new volume. This is volume. Our old volume is 2 liters. So what it's saying is that, oh, that's the wrong key to click. 3. And we take away 2, and we get 1.3 repeating. And that's the change in volume. That's a change in V. We have our new atmospheric pressure, 3 atmospheres. So we're going to do W equals negative 1.3333, our change in V times our pressure, which is 3. So this is 4 liter atmospheres. So we have to, so remember, this is liter atmospheres, not joules. Then we do the same thing again. So we have this. So let's put this in parentheses. We have this times, this is our new volume. And it was at 3 atmospheres divided by our new atmospheres, just 2. And we get our new, so this is always at 10 liters atmospheres, but whatever. Our new liters is 5, and our change in V is 5 minus this. So we have 1.6667. So now all we have to do is multiply the change in V, this, by the pressure, which is 2 atmospheres. So we're just going to add these together. And then we're going to multiply them by 101.3 to find the number of joules. So that's the right answer. I did not expect her to have a gas law. Not gonna lie. I did not. I was kind of blindsided by this and did not know how to do it. So keep the gas laws in mind. This is like the first gas law question we've had in 2 homeworks, but boy, is it there to catch us when we forget that it exists. So, excuse me. Fun. Anyway, the standard molar heat of fusion of ice is 60-20 joules per mole. Okay. So what's going on in this question, which I actually got wrong the first time? It's saying that we have our ice, right? We have our 1 mole of ice, and we're melting it. So this is endothermic. So our system is the 1 mole of ice, right? Heat has to go in to melt it. So Q is positive 620. Now, I don't know why, but it says 620 joules per mole, and it says we have 1 mole, so I'm presuming that's going to be positive 620. And then it doesn't mention that it's doing any work. And if you don't remember from the notes, unless something changes to or from a gas, so unless we have gas expansion or gas getting smaller, I don't know, concentration, I don't know, whatever. Unless it has to do with gases, when something is changing from one molecule to another, we act as though no work has been done. Of course, some work is going to be done, but I don't know how to calculate that, and we're not doing that right now. So just assume that it's 0. So just assume that W is equal to 0. So Q is positive, W is 0. So E, change in E, is going to be positive 60-20 joules. So that's the right answer. This one was kind of weird. I'm not going to lie. I didn't really like it. It was very odd, very confusing. But yeah, the water's under the gas phase. So yeah. Of course, realistically, some work was done. You know, it had to, the water's moving when it's melting the ice. But we have no way to calculate it, so it's just 0 for now. So this one was a little bit confusing. It wasn't too hard. It was just a lot of theory and lots of head scratching. So I hope this helps. Good luck on the test on Wednesday tomorrow. I'm going to be watching a lot of what should we call them? Lots and lots of lectures, because that's how I'm studying. So I wish you luck on your tests, and I hope this helped you figure out, and I hope you end up with a better grade on the homework than I did. Some of you did, I'm sure, but I did not. I think this is one of my lowest homework grades, which is really sad. Yeah, it's one of them. I had a couple 80s, so not really, but I've been doing pretty well in the last couple homeworks, so this is annoying. But I do hope that, I'm sorry, I wasn't really able to put this up yesterday, or make it yesterday, or even do I finished this last night, right? I was pretty busy Easter weekend, so sorry. But I do hope this helped, and I will see you guys next time we have a homework for me to help you out with. Bye-bye.